Have you ever really stopped to think about what's going on inside your phone or computer when it just does something? It seems like pure magic, right? Well, today we're going to pull back the curtain, and you'll see that it's not magic at all. It all comes down to a few super simple rules that, believe it or not, run our entire digital world.
Okay, so let's just dive right in with the biggest question of all. How in the world does a machine actually make a choice? I mean, it's just a bunch of metal and silicon. How does it decide to do anything, whether that's playing a song or just turning on a light?
The answer is way simpler than you'd think. It all just boils down to one thing: simple signals. And we're not talking about complicated ideas here. It's just on or off, yes or no. For a computer, that's a 1 or a 0. Seriously, that's it. That's their entire vocabulary. That's how they think.
All right, so computers think in ones and zeros. That sounds kind of, robotic and alien, right? But here's the thing, it's not. We actually use this exact same kind of logic constantly every single day. We just don't really think about it.
Just think about it. A traffic light. Green means go, red means stop. It's a simple binary choice. Or what about that little door ajar light on your dashboard? If a door is open, the light is on. If they're all shut, the light is off. See, computers are just taking that basic idea and doing it millions and millions of times a second.
So to handle all of these on and off signals, computers rely on these tiny, tiny little electronic switches. Billions of them, actually. And these aren't just any old switches. We call them logic gates. And honestly, they're the real fundamental building blocks of, everything digital.
And this right here, this really shows you the scale of it all. Everything, and I mean everything, starts with just 3 basic kinds of decision makers. They're called the AND, OR, and NOT gates. You take these gates, you put them together to build a circuit. You put a bunch of circuits together, and suddenly you have a CPU, the brain of your computer. But it all starts with these 3 simple guys.
Okay, let's meet our first building block. This is the AND gate. And let me tell you, this one is strict. The rule for the AND gate is simple. It will only give you an on signal if all of its inputs are also on. A great way to think about it is like a high-security safe that needs 2 keys. You need to turn key A and key B at the same time. Just one key won't cut it.
This little diagram shows exactly what I'm talking about. See those 2 switches, A and B? Those are our inputs. The light bulb is the output. Now look at the picture on the left. Switch A is closed, but B is open. The path is broken, right? So no power, light is off. But on the right, aha! Switch A and switch B are both closed. The path is complete, electricity flows, and the light clicks on. And this thing here? This is called a truth table. Don't let the name scare you. It's basically just a cheat sheet that shows all the possible outcomes for the gate. So remember, 0 is off, 1 is on. Just look down that output column. See all those zeros? The output is only, and I mean only, a 1 in that very last row. That one single situation where input A and input B are both 1. All right, next up we've got the OR gate. Now this one is way more laid back than the AND gate. Its rule is pretty simple. The output is on if at least one of the inputs is on. It's like getting off a bus, right? You can use the front door or the back door. Either one works, gets the job done. And you can see its circuit looks totally different. The switches are wired in parallel. What that does is it gives the electricity 2 different paths it can take. So all you need is for switch A or switch B to be closed, and boom, the circuit is complete and that light is going to turn on.
And yeah, the truth table for the OR gate shows this perfectly. The output is a 1 if A is 1, or if B is 1, or if they're both 1. Look at all those 1s. The only possible way to get a 0, to get an off signal, is if both A and B are 0, cutting off the power completely.
Okay, our last basic gate is the easiest one of them all. This is the NOT gate. It's got 1 input and it has 1 single job: to do the opposite. To flip the signal. We call it an inverter. You give it an on, it gives you an off. You put in a 0, it spits out a 1. Simple as that.
I mean, look at its truth table. It's tiny. If the input is 0, the output's 1. If the input is 1, the output's 0. That is literally all it does. But don't let that fool you. This simple little flip is absolutely crucial for building more complicated logic down the line. So there you have it, our 3 basic Lego bricks: AND, OR, and NOT. But, the real magic happens when you start snapping those bricks together. That's when we can create new, much more powerful gates and functions. For instance, what if you take the output from an AND gate and you plug it straight into a NOT gate? Well, you get a brand new gate called a NAND gate. It's literally not AND. And if you do the same thing with an OR gate and a NOT gate, you guessed it, you get a NOR gate. This is exactly how engineers build up all this amazing complex logic, starting with the absolute simplest pieces.
Okay, I know this can all feel a little abstract, diagrams and tables. So let's bring it back to the real world. How can we actually use these little gates to do something useful?
How about we build a simple home alarm system? Okay, so here's the problem. We need an alarm to go off if any of our doors or windows are opened. Just thinking about the gates we've learned, which one sounds like the perfect tool for that job?
If you said the OR gate, you're spot on. It's perfect. Think about it. The house is safe only when every single sensor is off, or 0. But the second that one window is opened, or the front door is opened, or the back door is opened, any one of those things turning into a 1 is enough to make the OR gate's output switch to 1, and beep, 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 the alarm goes off.
This simple sentence right here is the absolute heart of OR logic. When any window or door is opened, an alarm system will be on. Just one of those things needs to be true for the whole thing to become true. That's the OR gate in a nutshell.
Now, it's really important to remember something. We've been drawing these gates as these big, simple symbols on the screen. But in reality, we're talking about billions of these tiny decisions happening inside incredibly small components.
So this right here, this is an integrated circuit, what we call an IC, or just a chip. All that logic we've been talking about, the ANDs, the ORs, the NOTs, it's all shrunk down and etched onto this tiny piece of silicon. This little guy can hold millions, even billions, of those little switches all working together to make our gadgets go.
And really, that brings us to a pretty cool final thought. We've seen that even the most ridiculously advanced technology you could imagine is really just built on billions of simple, tiny yes or no decisions. And it kind of makes you wonder, doesn't it? What really complex problems in your own life could you solve if you could just figure out how to break them down into their simplest, most basic parts?